All right, so what we're going to talk about today is 15.3, conservative vector fields and independence of path, and the significance of that. Okay, and we've got a theorem here on page 1072, independence of path and conservative vector fields. So if f being your vector field, f is continuous. If it's continuous on an open connected region, then the line integral is independent of path if and only if f is conservative. Meaning, if you have a conservative vector field and you're going from one point to another point through a vector field on a connected region, so something like this, something that's connected as opposed to R2, which is not connected. So it has to be over a region that's connected, and then your f has to be continuous through that entire region. Okay, this integral, which again represents the amount of work done by the vector field in moving a particle along a specific path through that vector field, is independence of path if and only if f is conservative. Okay, so let's look at the beginning of this section, 15.3. So what they do is they show three different paths in example 1. So you've got this, find the work done by the vector field, by the force field, defined as this. Okay, again, what you're going to do that is the integral of w dot d, or integral work is the integral of f dot dr along a particular path. Now, in part A, you're going along the simple line y equals x from point 0, 0 to 1, 1. Notice these are all the same vector fields, okay, represented by this. Path 2 is along the line, the curve x equals y squared. So that's going from here to here along a different curve. And then the last one along y equals x cubed. So along this cubic function, but still from 0, 0 to 1, 1. And what you can see is that you have to reparametrize your curve for each of these different paths. So when you do an integral of f dotted with dr, you get a different function, you get a different integrand, but you get the same value for all three. Okay. In fact, what you find is that the path doesn't matter at all. What really matters is your endpoint and your beginning point. Okay. Nothing that matters along that path matters if it's a conservative vector field. So let's relate this to something that you did back in Calc BC. You had the fundamental theorem of calculus. Okay, when you evaluated the fundamental theorem of calculus, there was parts 1 and 2. I don't know what your book calls part 1 and part 2, but this is the one I'm talking about, is the integral from a to b of f of x dx. Okay, so you could either, what you'd have to do using the fundamental theorem of calculus is you find the antiderivative of f evaluated at b minus the antiderivative value of f of little f evaluated at a. And really, this integral was only dependent on your final and your initial points. Okay. Now, there's something called the fundamental theorem for line integrals. Fundamental theorem for line integrals. Okay, and it's similar, and it only works if it's a conservative vector field. So this is the integral of f dotted with dr. So this is the amount of work done by the vector field in moving a particle or an object along a particular curve or path through a vector field. So we'll say along some curve. And what this is going to be equal to is your potential function evaluated. Let's do this. Let's write it this way. X of b, y of b, minus your potential function evaluated at a, and y evaluated at a. Okay, so it's only dependent on your final minus your initial, which kind of makes sense if it's independence of path. Now, where does this come from? Well, let's kind of show a quick proof of why this is actually true. Remember, if f is conservative, this is only if your vector field is conservative. So if f is conservative, then the f can be written as the gradient of some other scalar function. Okay? And we can rewrite this as gradient of f dotted with dr. What we're really doing is we're dotting that with dr dt times your dt, okay? So by the chain rule, we can rewrite the dr as dr dt times dt, and this we can rewrite as the vector fx comma fy, okay? Because f is conservative, it can be written as the gradient of some scalar function, okay? And then dotted with this, and this thing is just your dx dt, dy dt, dt, and this is going to be evaluated from a to b. Now that we have the dt, the a and b are t values, which is why we have x of f of x of b, y of b, and f of x of a, y of a, because x and y are both defined as parametric functions of t, okay? So now this thing we can rewrite as from a to b. Okay, so we can rewrite this as, if we multiply this out, we get your fx dx dt plus your fy dy dt, okay, and that entire thing times your dt, okay? And by your chain rule, if you have a df dx dx dt plus a df dy dy dt, that's another way of writing df dt, integral from a to b, df dt, times your dt. Now you have an integral of a derivative, and when you take an integral of a derivative, by the other part of the fundamental theorem of calculus, that's equal to your f function evaluated at b, so x of b, y of b, minus your f evaluated at a, so x of a, y of a. Okay, so this right here is your fundamental theorem of calculus, our fundamental theorem for line integrals. Okay, so if you're evaluating the work done by a vector field and moving a particle along a particular path, if f is conservative, it's independence of path, so you don't even need to parametrize the curve because it doesn't matter. You need your final point and your initial point. In this f function, we've already practiced doing this. That's when you're finding the scalar function, your potential function for this vector field, where the gradient of this scalar function f is equal to this. Okay, so let's try a couple of examples. Actually, let's look at that example, that first example in your textbook. So it looks like every time they evaluated this along different curves, now we're not going to do this for those three, we've practiced that a lot in the last section, but they always got 1/4, 1/4, 1/4. Okay, so let's use the fundamental theorem for line integrals to evaluate and see if we also get 1/4. Okay, so our vector field is this. So this is example 1 on page 1069. Okay, so our vector field is equal to 1/2 xy, 1/4 x squared. Okay, and we're moving from 0, 0 to 1, 1. Okay, and those are x and y values. Okay, so let's look at how we would do this. The integral of f dotted with dr would be equal to, well, let's find our potential function, because this should be our potential function evaluated at 1, 1, the final point, minus our potential function evaluated at 0, 0. Now notice we don't have to call this x of a and x of b, x of b, y of b, and x of a, y of a, because we actually know the x and y coordinates. Okay, so if this thing, if f is conservative, this is an x derivative, and this is a y derivative. Okay, first, if we want to test that f is conservative, we would take the y derivative of this. So the y derivative of, sorry, it's really just the This would be your m. We want the dm dy. See if that's equal to the dn dx. So the y derivative of this is 1/2 x. The y derivative of this and the x derivative of this would be 1/2 x. Okay, so f is conservative. Okay, so what we're going to try to do is find our potential function. Okay, so potential function little f. So we know that an x derivative is equal to 1/2 xy. So we'll take the antiderivative with respect to x. So our f function as a function of x and y is going to be the antiderivative with respect to x. So that's going to be x 1/2 x squared over 2. So that's going to be x squared y over 4 plus some function of y. Okay, double check that. If you take the x derivative of this, we'll get 2xy over 4. That works. The x derivative of this, since this only has y's in it, we treat that as a constant, so we get 0. So let's find the y derivative of this, and then we're going to compare that to this over here that should be our y derivative. So the y derivative of this is going to be x squared over 4 plus g prime of y. Okay, and we're going to compare this. That needs to be equal to this, so that's going to be equal to 1/4 x squared. So these cancel, so we have g prime of y equals 0. So g of y, taking the antiderivative, would equal a constant. Okay, so plugging this back in here, we're going to get our potential function fxy is equal to x squared y over 4 plus our constant. Okay, so what we're going to do is we're going to evaluate this, and this is, we're going from the point 0, 0 to 1, 1. So evaluating this is going to be our f function evaluated at 1, 1 minus our f function evaluated at 0, 0. Well, here's our f function. Our f of xy is equal to, we said, x squared y over 4. You don't need the plus k. You could have the plus k. It's just going to subtract out. Okay, so we want f of 1, 1 minus f of 0, 0. So plugging in 1, 1, we're going to get 1 squared times 1 is 4. Minus 0, 0, we get 0. And what do you know? We get integral of f dotted with dr is equal to 1/4. Which is the same thing they got along all 3 of those paths. And we didn't use a path at all. We didn't parametrize a curve. We just said we're going from this point to this point along whatever path we wanted. Okay, so let's look. We're going to do a couple more examples. Actually, I want to talk about the fundamental theorem for line integrals. Okay. Oh no, we already talked about that. We talked about where this came from. I'm looking right here. We did talk about this proof. Perfect. Okay, we're going to look at example 3. So example 3 in the book looks like this. Using the fundamental theorem of line integrals, evaluate this, where C is a piecewise smooth curve from this point to this point, and there's your vector field. Okay, so this is example 3. I started to write this down. Our vector field is equal to 2xy x squared plus z squared 2yz. Okay, if you don't feel like you need to do this example, you don't need to do it. We're going from this point to this point, which is what they said right here, right? I wrote that down correct. Okay, so evaluate this. Now, first of all, we don't really have a path here. We don't have a specific path. And if this is not a conservative vector field, then this integral is going to be different on different paths. But we can first see if this is a conservative vector field. So let's test that. You remember how to test if this something in 3 dimensions is a conservative vector field. Okay, what we do is we find the curl of f. So the curl of f, so this is good practice to remember how to do that. We do this thing crossed with our vector field. That's an I, a J, and a K, a ddx, a ddy, and a ddz. And then we've got the 2xy. We've got x squared plus z squared. We actually might have already done this one in the previous section, but it's good practice to do it again. So in the I direction, we get the y derivative of this. So 2z minus the z derivative of this, 2z. In the j direction, we do this minus this, but we make it negative. So I'm going to switch. The z derivative of this is 2x minus the x derivative of this. The z derivative of this is 0. Z derivative of this, there's no z's in it, so that's 0. And then the x derivative of this is 0. And then the k direction, we do the x derivative of this, which is 2x, minus the y derivative of this, which is 2x. And we get the curl of f is equal to 0, 0, 0, which means f is conservative. Therefore, f is, in fact, conservative. Now we have to find our potential function. Okay. If f is conservative, we know this is an x derivative, this is a y derivative, and this is a z derivative. So going through this process one more time, we've got our fx is equal to 2xy. So let's take the antiderivative with respect to x. Our f, which this time is a function of x, y, and z, is going to be equal to the antiderivative with respect to x is 2x squared over 2. So we get x squared y plus g, which now can have y's and z's in it. Okay, let's take the y derivative, which is going to be x squared plus gy of yz. Y derivative x squared plus gy of yz, which has to match the y derivative here if this in fact is conservative. So that's going to be x squared plus z squared. So now the x squareds cancel, and gy of yz is equal to z squared. Let's take the antiderivative with respect to y. So g of yz is equal to yz squared plus your constant, but your constant could have z's in it. So let's call that h of z. And this we have to, no, don't do that yet. But now what we want to do is take the z derivative. Oh, don't do that yet, sorry. We want to take this thing, which is our gy of yz, we're going to plug it back into here. So now our function f of x, y, z is equal to x squared y plus yz squared plus h of z. And now we take the z derivative of this so we can compare that to what our z derivative needs to be, the 2yz. So the z derivative of this, fz, is going to be equal to, that goes away. We've got 2yz plus the derivative of this, h prime of z. That has to equal this 2yz, which needs to be our z derivative, 2yz. Okay, so these cancel and we get h prime of z equal to 0. So h of z is just a constant. Sorry, h of z is a constant. And that we're going to plug back in to here. And we've got our potential function. Our potential function is right here. So f of x, y, z equals x squared y plus yz squared plus our constant. There's our potential function. Okay, and since this is conservative vector field, actually I always like to double check, make sure I did that right. The x derivative of this is going to be 2xy. That works. The y derivative should be x squared plus z squared. That works. And then the z derivative should be 2yz. That works. Okay. So it's pretty easy to double check that you found this potential function correctly. Okay. Now your integral of f dotted with dr is equal to your f This function evaluated at your final point, 0, 2, 3, minus your f evaluated at your initial point. Initial point was 1, 1, 0. Okay, which is equal to f of 0, 2, 3. So this first term is 0 because x is 0. This one's going to be y times z squared, so 2 times 9, 18. You could do plus k if you want. You don't need that. It's going to subtract out. Now plugging in 1, 1, 0. So this one gives you 1 squared times 1. 1 plus, that's going to be yz squared. Y times z squared, that's going to be 0. And then you got your plus k. Okay, so I've got 18 minus 1. I got 17. Let's just double check our book. This was example 3. Did we do that right? 17. Yes, that is correct. Okay, so that's example 3 on page 1071. Let's look at example 4. Okay, example 4. You can look at it in your book, but I've written it down on 1073. So your vector field is this. You have just x, y, and a z. Find the work done by F in moving your particle, moving an object along a curve from here to here. Notice it doesn't tell you the curve. Let's see, example 4. Why did I want to do this one? Yeah, so this is basically exactly what we did last time. If you want, you can fast forward through this one. I'll do this one, but if you want to see another example, I'll do it. And then I'm going to do example 5. Example 5 is kind of interesting. Okay, so this one, first of all, we have to test if this is conservative. So we have to find the curl of F. Okay, so I've got I, J, K, the ddx, the ddy, and the ddz. And then I've got e to the x cosine y, negative e to the x sine y, and 2. Okay, so I want the y derivative of that, 0, minus the z derivative of that, 0. Doesn't that work out nicely? In the j direction, I've got this minus this, the z derivative of that is 0, minus the x derivative of that is 0. And then in the k direction, I've got the x derivative of this, which should be negative e to the x sine y minus, and I want the y derivative of this. The y derivative of this is going to be e to the x sine y. X sine y. Let's see what I do. So in the k direction, oh, I want the negative e to the x sine y minus, oh, this is negative. So minus a negative, that becomes positive. Okay, so you do in fact get 0, 0, 0. Okay, so the curl is 0, which we know f is conservative. So what we're going to do is find our potential function, meaning this thing has to be an x derivative, this thing has to be a y derivative, and this thing has to be a z derivative. Okay, so I'm going to start with fx. So find your potential function, little f. Okay, so I've got my fx is equal to e to the x cosine of y. Take the antiderivative, so f as a function of x, y, and z is going to be the antiderivative with respect to x, which is simply e to the x cosine y, okay, plus some function of y and z. Let's find a y derivative of this so we can compare that y derivative to what this y derivative needs to be. Okay, so my y derivative is going to be e to the x times negative sine y plus the y derivative of yz. And that has to be equal to my y derivative up there, which was e to the negative e to the x sine y. So those cancel. I've got g, the y derivative, equals 0. So g of yz equals a constant. Let's plug that back in up here. Now my function f of x, y, z is equal to e to the x cosine of y. Oh, let's see what I do wrong. The y derivative is this. The y derivative is 0. So g of y z equals k. Oh, yeah, plus k. Okay. Now what I'm going to do is find the... oh, sorry. It's not just k. Yeah, let's fix that. Okay. So this is a function of y and z. If I take the antiderivative with respect to y, this could have z's in it. So this is going to be h of z. Okay. Because if you take the y derivative of this, you get 0. And anything that has a z in it, we're treating z as a constant, so that would be 0. So I've got plus h of z. Okay. So there's my function. Now I'm going to find the z derivative. The z derivative equals h prime of z. Okay, and the z derivative up here has to equal 2. So that has to equal 2. H prime of z equals 2. So h of z equals 2z. So my function, plugging that back in up here, I've got f of x, y, z equals e to the x cosine y plus 2z. Okay, I like to try to find the x derivative. It's e to the x cosine y. That works. Find the y derivative. E to the x times negative sine y. That works. And then the z derivative is 2. Perfect. Okay, now what we're doing is we're plugging in, we're finding the work done, we're finding integral of f dot dr. There we go. And moving an object along this curve. Now we can simply use the fundamental theorem for line integrals because it's conservative. We proved it's conservative. The curl is 0. Okay, so I'm going to plug in these two ordered pairs into my function. Okay, so I'm finding f of 1 pi 3 minus f of 0 pi over 2 comma 1. Okay, I'm plugging in, so I get e to the 1 cosine of pi plus 2 times 3, then minus, plug in a 0 for x, I'm going to get e to the 0, which is 1 cosine of pi over 2 plus 2 plus 2. Okay, so that's e times cosine of pi, so that's negative e plus 6. And then I get minus cosine of pi over 2 is 0, so minus 2. And I get 6 minus 2, 4 minus e. Okay, that was an interesting problem, 4 minus e, which is correct. Okay, now let's look at the final example we're going to do together. This one I like because they show you different ways to do this problem. Okay, now I'm looking at example 5. If you look in the book, they give you a picture, evaluate f dot dr, where f equals this, and you've got a semicircular path from 0, 0 to 2, 0. They tell you to go along this path from 0, 0 to 2, 0. Fine, we can go along that path. Okay, but if this is independent of path, maybe I want to pick an easier path. Maybe I'm like, okay, the integral is going to be a lot easier if I use this path. Can I use a different path? Well, sometimes, if it's a conservative vector field, you can use any path you want. So you don't have to use that path. Okay, so there's 3 ways we can do this problem. Okay, we can use the path they told us and just evaluate the line integral, f dot dr. Okay. If this is a conservative vector field, so we have to test to see if this is conservative. If it's conservative, we can pick an easier path. Okay. If it's conservative, we also can use no path at all and use the fundamental theorem for affine integrals and just use the final and the initial points. Okay, so let's do all three ways. Well, first of all, let's find out if this is a conservative vector field to see if we have those options. If it's not conservative, you have to use the path that they told you. Okay, so is this conservative? Remember, this thing is m and this thing is n. There's only two dimensions here. So is dm dy equal to dn dx? That will tell us if this is conservative. So the y derivative of this is 3y squared. The x derivative of this is 3y squared. So f is conservative. Okay, let's do this in three ways. So part A, we're going to find integral of f dotted with dr along the path they told us, the semicircle. Okay, so we have to parametrize this curve. So if you simply had, and this is a little tricky, if you simply had a circle, the way you parametrize a circle is x equals cosine t, y equals sine t, and that's going to assume you're going in this direction, right? And now this is tricky because we're not going in that direction, we're going the opposite direction. So our cosine is going in the opposite direction. So it's actually going to be x is equal to negative cosine t. Now the sign doesn't matter. We can say y equals sine t, because whether you're going this way or this way, your y values start at 0, go up to 1, back to 0, down to negative 1. If I start here and go in this direction, doesn't matter. Start at 0, up to 1, so the sign doesn't change. Now, I also moved this circle. This circle is now centered at 1, 0. Okay, so this x has to turn into, if I shift it 1 to the right, that turns into x minus 1 equals negative cosine t. And then y is equal to sine t. Okay, so the way I'm going to parametrize this curve is x equals 1 minus cosine t and y equals sine of t. And let's double check that that works. When t is 0, we should be at the point, let's see, did I do this right? When t is 0, we should be at 0, 0. Okay, so 1 minus cosine of 0, cosine 0, 1. So that's correct. Sine of 0, and we'll say this is going to be t goes from 0 to pi. So when t is 0, I'm at the point 0, 0. When t is pi, cosine of pi is negative 1. So 1 minus negative 1 is 2. So that makes sense. At this point, I should be at 2. I should be at 2 comma 0. And sine of pi is 0. So that works. Okay. So now I'm going to evaluate this the way we did in the last chapter. Remember how we evaluate f dotted with dr. Okay, it's the integral of f of r of t dotted with r prime of t dt. Okay, because remember that this dr is, it's really a dr dt times the dt. Okay. And so this is going to be, our f function is y cubed plus 1 and 3xy squared plus 1 dotted with, and now I need a dx dt and a dy dt, and t is going from 0 to pi. Okay, so my r of t is equal to this thing. This is the path that I define. And my r prime of t is equal to, well, that's going to be positive sine t, and this is going to be cosine t. Okay, now let's integrate. Before we integrate, we have to replace y. Well, my y value is sine of t, so this is going to be sine cubed t plus 1, comma, that's going to be 3 times Ugh. 1 minus cosine of t times sine squared t plus 1 dotted with dx dt. Dx dt is sine t. dy dt is cosine t. And we've got our dt here. Okay, so now we've got to, wow, this gets messy. Okay, but you can see, it's funny what they say in the book, because we could do this. You'd have to multiply all that out. You'd have to do the dot product. The book, they got jokes. They say once they get that calculate this integral should dampen your enthusiasm for this option. So we're not going to kill ourselves on this option. We got 2 other options that are going to be better. Okay. Our next option, since it's a conservative vector field, which means this integral is independent of path, I could pick a different path. I could pick this path right here. I could parametrize the line segment from 0, 0 to 2, 0 and just go straight across this way. Okay. So option 2, along segment 0, 0 to 2, 0. Now, when I do any kind of a line segment, I like to do r of t equals r of 0, my initial one, plus your t times your vector that gets you from here to here. So that's going to be the vector 0, 0 that gets you to this initial point, plus t times the vector 2, 0. Now, whenever you do it this way, your t is always going from 0 to 1. Okay, so my r of t equals this. So r of t equals, your x is just 0 plus 2t. Your y is 0 plus 0t. And t goes from 0 to 1. So when t is 0, you're at 0, 0. When t is 1, this is linear, and you get to the point 2, 0. Okay, let's do r prime of t. And that's going to be 2, 0. So this is easier. Now your x value, if you write this in parametric equations, x of t is simply equal to 2t, and y of t is equal to 0. Okay, so when we go to evaluate this integral of f dotted with r prime of t dt, so your f is y cubed plus 1, 3xy squared plus 1, dotted with r prime of t, which is 2, 0, dt, from 0 to pi. Okay, now let's simplify this because I know that my y value is 0, so all the y's are 0. So that's just going to be 1, comma, that's 0, 3 times 2t times 0. 1, 1, dotted with 2, 0. Oh, that's a much better integral from 0 to pi. So that dot product is 2 dt going from 0 to pi, which is going to give you 2t from 0 to pi, so you get 2 pi. Okay, double check that. Oh, it's not 0 to pi, sorry. That's a mistake. Okay, remember our t goes from 0 to 1. Okay, this integral we want from 0 to pi, so just 0 to 1. Okay, so from 0 to 1, which means you don't get 2 pi, you simply get 2. So 0 to 1, 0 to 1, 2 times 1. So this integral is 2. Remember, our t goes from 0 to 1. Because we took a simpler path. That was a much better integral. Okay. Now let's try using the fundamental theorem for line integrals. Okay. Now we're not even going to do, we're not going to parametrize the curve at all. We don't have to. Okay. But what we do have to do is find our potential function f. Okay. So our vector field is this thing, y cubed plus 1, 3xy squared plus 1. Okay, so this thing is a x derivative. So an fx. This thing is a y derivative. Okay, so fx equals y cubed plus 1. Take an antiderivative, so that's going to be xy cubed plus x. Okay, plus some function of y. Double check that. If you have this, you take an x derivative, you get y cubed plus 1 plus 0. Okay, now we're going to take a y derivative. Fy equals 3xy squared, that goes away, plus g prime of y, and this has to match this thing, so it has to equal 3xy squared plus 1. 3xy squared and 3xy squared, subtract those, g prime of y is equal to 1, so g of y equals y. Plug that in here, and you've got your potential function. So f of xy is equal to xy cubed plus x plus y. Double check. Your x derivative should be y cubed plus 1. It is. Your y derivative should be 3xy squared plus 1. It is. Okay. So now what we're doing is we're evaluating this function. Remember our fundamental theorem for line integrals. Integral of f dotted with dr is equal to your f evaluated at your final minus initial. Okay, and here they gave us, I think, the ordered pairs, right? The ordered, yes. We were looking at this point. So we have to evaluate at 2, 0 minus at 0, 0. So f evaluated at 2, 0 minus f evaluated at 0, 0. And we know we should get what we got when we did this direct path. We should get 2. Okay? Remember, this is our function f. So if we plug in a 2 for x and a 0 for y, we're going to get 0 plus 2 plus 0 minus, and plug in 0, 0, 0, you get 0 plus 0 plus 0, and we simply get 2, which matches. Okay? So that's all for today. Just do the problems that I assign on the assignment sheet. And I will see you all tomorrow.